Balancing Single and Double Replacement Reactions by Mrs. Felicia. Single replacement reactions. I can recognize single replacement reactions when I have one molecule replacing another in a compound. In this case, I have selenium hexachloride and oxygen reacting to form selenium oxide and chlorine. Here, the oxygen will kick out chlorine and take its place. The chlorine will then be free to do whatever it does. We set up our equation and list the elements. We list the initial number of atoms on both the reactant and product sides. Listing out how many atoms of each element I have on each side of the equation lets me see how I have only one thing to do. The selenium and the oxygen are the same on both sides. The only coefficient I need to add is 3 to balance the chlorine. I update my atom counts. Everything adds up as it should. Now my equation is balanced. I can recognize single replacement reactions when I have one molecule replacing another in a compound. In this case, I have magnesium and zinc phosphate reacting to form magnesium phosphate and zinc. Here, the magnesium will kick out the zinc and take its place. The zinc will then be free to do whatever it does. We set up our equation and list the elements. Hey, wait a minute! What do I do with the parentheses? Listing the magnesium and zinc is exactly what you're used to. Listing the phosphorus and oxygen is a little different because phosphate is a polyatomic ion. Here we have two polyatomic ions in both the reactants and the products. We multiply each element that makes up phosphate by its subscript as shown. As I look at my counts, I notice that everything is equal except for the magnesium atoms. I update my atom counts. Everything adds up as it should. Now my equation is balanced. Did you know there's another way to work this problem? I'm about to show you. Because phosphate is a polyatomic ion, we can keep it as a unit in our calculations, so I can alternatively do the atom counts as shown. When we look at it this way, all we really need to do is to change the coefficient of magnesium to 3. I update my atom counts. Everything adds up as it should. Now my equation is balanced. Double replacement reactions. I can recognize double replacement reactions when I have two compounds that each gives up a component of itself to trade with the other. This reaction yields two different compounds. In this case, I have hydrogen phosphate and potassium hydroxide reacting to form water and potassium phosphate. During this reaction, the phosphate ion breaks apart from hydrogen to join with the potassium from the potassium hydroxide, which forms potassium phosphate. Likewise, the hydrogen from the hydrogen phosphate joins the hydroxide to form water. We set up our equation and list the elements. I remember that PO4 is a phosphate ion, so I can list it as a unit. We list the initial number of atoms on both the reactant and product sides. Whenever I have the same element in more than one molecule or compound, I keep a running total as I work. I think of PO4 as phosphate. I'm thinking of it as a unit. The phosphate on the product side needs 3 potassium atoms instead of just one, so I will start there. I will add a coefficient of 3 in front of the potassium hydroxide.
I update my atom counts.
If I add the coefficient of 3 to the water molecule on the product side, I will have balanced my equation.
I update my atom counts.
Everything adds up as it should. Now my equation is balanced.
Be sure to ask your teacher if you still don't understand something.